A very good morning to all of you. Today's lecture will deal with basic introduction and preliminaries in analog and digital pulse modulation schemes. We know that many signals in modern communication systems are digital. Also, analog signals are transmitted digitally in order to reduce distortion and in order to improve the signal to noise ratio. Some of the techniques that we use for digitization digital modulation are pulse amplitude modulation, pulse width modulation, pulse position modulation, basic pulse code modulation techniques, and delta modulation that we are going to have a look on. First of all, why do we require pulse modulation? That needs to be understood. In continuous wave modulation schemes, some parameter of modulated wave varies continuously with message, and that results in improved performance in terms of noise reduction. In analog pulse modulation, however, some parameter of each pulse is modulated by a particular sample value of the message. Uh, Thus, we can classify pulse modulation into two types basically. One is the analog pulse modulation, another is digital pulse modulation. And we should look how many schemes which are popular come under analog pulse modulation scheme and how many come under digital pulse modulation scheme. We will come to know that pulse code modulation PCM, delta modulation DM, and some other variants of delta modulation that like adaptive delta modulation, etc., come under digital pulse modulation. Apart from that, pulse amplitude modulation, pulse width modulation, and pulse position modulation fall under the category of analog pulse modulation. So if someone presents you with the output signal of a modulation scheme, just because it looks like a pulse, it doesn't mean a digital signal. There is something more for a signal to be termed as a digital signal. Before we go on to digital pulse modulation scheme, let's have a look at some analog pulse modulation scheme because the idea of sampling and reconstruction and digitization is intricately related to all these ideas. Pulse amplitude modulation in this scheme, some high frequency carrier pulse is varied in accordance with sampled value of message signal. In pulse width modulation, the width of the carrier pulse are varied in accordance with the sampled value of message signal. You can see the third graph in purple color on your screen. That's the example of pulse width modulation. For example, speed control of DC motors is accomplished using pulse width modulation. Also, output signal processing of sensors and actuators is done using pulse width modulation. Any physical quantity, when converted into its electrical equivalent, needs to vary, and this variation, more often than not, is done in the form of width of the pulse that is being generated. Third example is pulse position modulation. In this scheme, position of high frequency carrier pulse is changed in accordance with the sampled value of message signal that you can see as the fourth graph on your screen. Now, PCM is the most basic digital modulation technique which involves three basic steps. First is sampling, second is quantization, and third is binary encoding. When all these three steps are completed, only then an analog signal can be said to have been converted into a digital one. Before sampling, the signal is filtered to limit bandwidth. Bandwidth plays a very important role because it might result in distortion in the output digital signal that is generated before or after transmission. Now what is sampling? Sampling is process of converting analog signal into discrete signals. Note the use of the word discrete instead of digital because there is some confusion in the beginning among students regarding a signal being discrete or a signal being digital. When you sample an analog signal, it becomes a discrete signal, not a digital one. It becomes digital only when The process of quantization and binary encoding are complete. Sampling is common in all pulse modulation techniques. The signal is sampled at regular intervals such that each sample is proportional to amplitude of signal at that instant. Analog signal is sampled every say ts seconds called sampling interval, where the reciprocal of this particular value is called the sampling frequency or sampling rate. And we know that fs is equal to 2 fm, where fm is the maximum frequency component in the signal, is the minimum sampling rate. It is also called the Nyquist rate. Sampled spectrum in the frequency domain, denoted by g omega, is repeating periodically without overlapping when we sample at a rate equal to or more than the Nyquist rate, which is 2 fm, where fm is the maximum frequency component present in the signal. Original spectrum is centered at omega, which is 2 pi f is equal to 0 and having bandwidth of omega m. Spectrum can be recovered by passing through low pass filter with cutoff omega m. For sampling frequency smaller than twice of the maximum frequency, sampled spectrum will overlap and cannot be recovered back. This is called aliasing. We need to avoid this situation. This picture graphically represents aliasing. This signal is the alias signal, where you can see there is a significant overlap because the sampling has been done at a rate lower than twice fm or lower than the Nyquist rate. Note where the individual bands are centered. They are centered at fs and integral multiples of fs, both in the positive and negative direction. This is the spectrum of the sampled signal. Now, if we want to represent it mathematically, in time domain, let S be the input analog signal, and if we want to sample it, we need to use a sample pulse train. If we multiply the signal with the sample pulse train, then we can get sampling at that particular instant of time. This pulse train is nothing but a series of delta functions which occur at regular intervals, and this interval is given by integral multiple of this sampling time ts. That's why delta t small t minus n capital Ts gives you a particular sample, a particular delta function shifted from the center or from the origin at a value which is integral multiple of sampling time. If we sum it from minus infinity to infinity, we get the sample pulse train extending in both directions from plus infinity to minus infinity. This sample pulse can be represented as a Fourier series like equation 2, where each component has been represented as a sinusoidal multiple. When we multiply the original message signal ST with this Fourier representation of sample pulse train, it becomes ST multiplied with the sampling frequency and 2ST multiplied with the sampling frequency and the sinusoidal harmonics. This is the sampled output signal that we are interested in. We expect that if we take the inverse Fourier transform, we can recover the whole original signal. This is in the time domain. Now, sampling of band pass signal, the signals which are limited in a particular band. A band pass signal of bandwidth 2 FM can be completely recovered from its samples. However, Nyquist criteria should hold. Minimum sampling rate should be 2 into the bandwidth, which is 2 into the twice FM according to Nyquist criteria. That makes it 4 times the maximum frequency component. Range of minimum sampling frequency is in the range of 2 into the bandwidth to 4 into the bandwidth. Remember that this is different from the case when we are sampling a baseband signal or a low pass signal which extend from 0 to a particular frequency. In that case, the minimum sampling rate is not 2 into bandwidth, it is just 2 into maximum frequency component. So this is the difference between sampling of a baseband signal and a band pass signal. Range of minimum sampling frequencies is also different, which is 2 into bandwidth in the case of band pass signal, and in the case of low pass signal or baseband signal, it should be 2 into bandwidth. Instantaneous sampling or impulse sampling, these are two variants of the sampling strategy. Sampling function is basically a train of spectrum which remains constant impulses throughout frequency range. But however, practically we can't generate such kind of constant impulses throughout the whole frequency range. We have natural sampling where this spectrum is weighted by a sinc function. In this, amplitude of high frequency component reduces. And again, we have flat top sampling where the top of the samples remain constant. In this spectrum, high frequency components are attenuated due to sinc pulse roll off. This is known as aperture effect. In order to better understand aperture effect, first let's have a look at three different sampling methods. This is the ideal sampling. However, it is not easy to generate, not practical to generate ideal sampling. Natural sampling is in the right hand side figure, and on in the bottom figure we have indicated flat top sampling. If pulse width increases, aperture effect is more in flat top sampling, that is more attenuation of high frequency component. This happens because you see the extension of this particular this particular pulse that you see on your screen in time domain is ht, which extends from 0 to tau. In frequency domain, its spectrum you can see is a sinc function, resembles a sinc function. Hf is in the frequency domain. Now, attenuation of high frequency component is dependent upon the width of this particular pulse. So if this extension 0 to tau is more, there will be more attenuation of high frequency component. And that can be understood using this mathematical treatment. Let the spectrum of a flat top sample signal is expressed as GF. It's a spectrum, so it's in frequency domain, is equal to Fs is equal to the summation of x into HF, where we can assume that this whole process is like transferring this ST signal from a low pass filter HF, which gives us the GT. So the transfer function is HF and it resembles this sinc function. Now this HF is given by tau sinc f tau e raised to power minus j pi f tau, and this transfer function has a component. We are assuming that the area under that particular curve is 1. That's why we are with this equation where tau, if you increase it, you are going to increase its amplitude also. We need to have a particular equalizer since we are assuming that the message signal xt or xt is transferred to a low pass filter with transfer function hf. The transfer function of this filter is given as equation 2. So in order to compensate for the loss of attenuation of the high frequency component, we need an equalizer, what we know as an equalizer. An equalizer is a device which is used in cascade with this reconstruction filter. It decreases the in-band loss of this reconstruction filter. So what we are doing, we are calling this HF as a reconstruction filter, as the aperture effect, that is the effect of attenuation of higher frequency component when the pulse width is large in flat top sampling. This aperture effect is reduced. So what is the transfer function of the equalizing filter or the equalizer? This transfer function is given in equation 3, where k is a constant, and in order to cancel out, we have the denominator equal to the transfer function of the reconstruction filter, and where the introduction of this equalizer introduces a delay TD. This delay is introduced by this low pass filter HF, and the amount of this delay is tau upon 2. So if you put tau upon 2 in equation 3, the exponential term is going to cancel out if we also put HF is equal to RHS of equation 2. So what we have remaining is the transfer function of the equalizer, which is equal to k upon tau sinc f tau. So this particular signal reconstruction filter analysis is important to estimate the aperture effect and what equalizer we require in order to compensate it. What happens when aliasing occurs? Waves of higher frequency are recorded as lower frequency. That's the another statement for what I have discussed about the aperture effect. According to the sampling theorem, the input of an analog to digital converter requires a low pass analog anti-aliasing filter. And for this reason, the sampled input signal must be band limited to prevent aliasing. That is why the output of our DAC requires a low pass analog filter called a reconstruction filter. So that was the same reconstruction filter that we have analyzed in here. And how should the transfer function of this reconstruction filter look like? This reconstruction filter should make the output signal band limited. It should prevent imaging, and Fourier coefficient are reconstructed as high frequency mirror. This required implementation of a particular interpolation formula. And in order to implement all these recommendations, what we came up with was some salient features of reconstruction filter, that it should be a brick wall filter. It should have a constant phase delay, and this constant phase delay have been denoted in the analytical treatment using the term TD. It should have constant flat frequency response and zero response from the Nyquist frequency. So what kind of a filter is the best candidate? So we have our sync filter is the best candidate for a perfect reconstruction filter. So what happens, that we have this pulse amplitude modulated signal. It has some noise components also in it. It is passed through this reconstruction filter having the transfer function sync, and then it is passed to the equalizer whose transfer function we have derived just now, and then at the output of it we have the original time domain message signal. This receiver contains a low pass reconstruction filter with cutoff frequency slightly higher than the maximum frequency present in the message signal. The equalizer then compensates for the aperture effect. It also compensates for the attenuation by a low pass reconstruction filter. In the next lecture, we will deal with quantization and encoding. Thank you.